Saturn has a small moon that looks completely dead. 400 kilometers across, made of ice, covered in craters. One crater is so large it gives the whole moon a shape people recognize immediately, the Death Star. That part's coincidence. The crater is real. For decades, Mimas was the easy moon to explain. Cold surface, frozen interior, a quiet record of ancient collisions, nothing going on. And then a NASA spacecraft called Cassini found a wobble. The moon rocks slightly as it orbits Saturn, more than it should, more than a frozen solid object produces. When researchers went back through the data in 2024, a second independent measurement pointed the same direction. Mimas may be hiding a global liquid ocean, 20 to 30 kilometers beneath that dead-looking surface, right now. Active, young. We don't have a photograph of it. No probe has sampled it directly. The entire case rests on how this moon moves, not on what we can see. So we're looking at the most crater-scarred, apparently finished surface in the solar system. And it may be the most misleading one. By the end of this video, you'll understand the evidence for that ocean, where it's solid, where it's inferred, and why, if Mimas really does have one, it changes where we think to look next. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Saturn has dozens of moons. A handful of them are large enough to round themselves into spheres under their own gravity. Mimas is the smallest of those, and it is a quiet object, about 394 kilometers across. That sounds large until you remember that Earth's own moon is more than 9 times wider. Mimas would fit comfortably inside many countries. A small world, and it is cold. Out at Saturn, sunlight is feeble. The surface temperature on Mimas sits near -200 degrees Celsius. Water at that temperature is not liquid. Water there behaves like rock. The whole moon, on the outside, behaves like stone. Now look at the surface. Craters everywhere. Old ones, new ones overlapping older ones. Some sharp at the edges, some softened by time. Barely a stretch of terrain that hasn't been hit by something. So Mimas's surface looks like a record. From orbit, the entire face is a layered history of impacts. And here's what that record tells us. In planetary science, we read craters as a kind of clock. A surface with very few craters is usually young. Something has erased the older marks. Flowing ice. Geological resurfacing. Internal heat working its way to the outside. A surface like Mimas's is the opposite. Heavily cratered, densely cratered, cratered down to small scales. The simple reading is that Mimas has been sitting still for a very long time. Whatever happened to it happened, and then nothing came along to wipe the slate clean. Now think about how that reading is actually made. Scientists don't just glance at a moon and call it old. We map the craters across regions of the surface. We tally the sizes. We compare the distribution to known impact rates over the history of the solar system. The result is a statistical age estimate for that piece of terrain. On Mimas, the cratering statistics consistently come back as old, not patches of old surface scattered among younger ones. Old, more or less everywhere. So the early picture wasn't built on one image. We built it on a quantitative reading of the whole face of the moon, repeated by different teams, returning the same general answer. And then there's Herschel. Herschel is the crater that gives Mimas its visual identity, about 130 kilometers wide. On a moon less than 400 kilometers across. That is enormous. The crater takes up a noticeable fraction of one face. Its rim is high, its center is marked by a tall central peak. Whatever struck Mimas to leave Herschel came close to breaking the moon apart. Look at Mimas with the right lighting, and the silhouette resembles a fictional space station from a famous film. The resemblance is a coincidence of geometry, a round body, one vast crater. The eye does the rest. But Herschel isn't just a thumbnail. It's a piece of evidence. A crater of that scale, preserved on a small, icy moon, tells us something about the body that holds it. Big basins on warmer or weaker worlds tend to soften. They sag. The walls slump. The floor rises. Over long enough time, a basin can almost vanish. On Mimas, Herschel still looks sharp. The rim is intact. The relief is preserved. So for a long time, Herschel was treated as confirmation of the simple story. Mimas is small. Mimas is cold. Mimas is rigid. The crater stayed because the moon never had the warmth to erase it. And there was nothing else to argue otherwise. No plumes, no fresh terrain, no glowing pockets in thermal images, no streaks of bright young ice, no fractures cutting cleanly across older craters, none of the things that would normally announce a moon with internal life. Now think about how different that picture looks from the moon next door. Enceladus, just a little further out, sprays water into space. We can see the plumes, we can sample them. The surface is split by long parallel cracks called the tiger stripes, where warm material reaches the cold outside. There's no ambiguity about Enceladus. It's alive in the geological sense. It's doing something now. Mimas, in comparison, looked like a museum. So scientists settled into a working picture. A small icy moon, frozen through, geologically inert, sitting quietly in Saturn's orbit. Its main interest was its history of impacts and its role in shaping Saturn's rings. As a candidate for hosting a hidden ocean, Mimas sat near the bottom of the list. But here's the catch. Mimas is also a moon being pulled on by Saturn. The same gravity that keeps it in orbit also stretches it slightly. It flexes the body as the moon moves. That flexing on other moons can heat the interior. It's the basic engine that keeps Enceladus warm. And Mimas, by some calculations, sits in conditions that should not let it be ignored entirely. Yet for years Mimas seemed to ignore them. The surface stayed quiet. The crater record held. The simple reading held with it. So what no one could see, from the surface alone, was the inside. And here's the part that mattered. A heavily cratered shell does not necessarily prove that nothing is happening underneath. It only proves that nothing has been happening long enough to reshape the outside. Those are not the same statement. Subtle changes in a deep interior can take a long time to leave a fingerprint on the crust above. If the changes are slow, or recent, or both, the surface may simply not have caught up. But we didn't have a way to test that at first. The tools were images and basic shape data. The surface was what we could see, and the surface said, dead. Now think about the thermal logic that made this so convincing. Small icy worlds in the outer solar system have a limited budget for internal heat. When they form, they carry some radioactive elements inside, elements that decay and release warmth over time. But for a body as small as Mimas, that budget runs down quickly. On geological timescales, radioactive decay alone cannot maintain a liquid layer. So for a body this small, the question of whether any liquid exists on the inside reduces to a question about other heat sources. And the most obvious other source, tidal heating, seemed, based on the surface, to be doing nothing. A heavily cratered, undisturbed shell was exactly what you'd expect from a body that had been losing more heat than it was gaining for billions of years. Cold at the surface, cold on the inside. That was the picture the surface seemed to confirm in every direction you looked. Cassini changed the size of the question. The mission spent more than a decade in orbit around Saturn. It mapped Mimas in more detail than any spacecraft before it. It tracked the moon's motion. It measured how Mimas turned and tilted as it moved through its orbit. It collected the kind of data that no still image could give. Now think about what a multi-year orbital mission can do that a flyby cannot. Voyager passed through the Saturn system in 1980 and 1981. Those flybys gave us our first real look at Mimas as more than a point of light. They produced images that immediately suggested a small, scarred, geologically inert world. For the next 2 decades, that was the picture we had to work with, so Cassini, arriving in 2004, refined and deepened it. The same surface story came back at higher resolution. the same crater dominance, the same preserved relief on Herschel. Better images, more details, the same broad answer about the kind of body we were looking at. But Cassini did something Voyager couldn't. It came back to Mimas, repeatedly, from different angles, across many years. That repetition made fine precision measurements of motion possible. A flyby gives you one snapshot. Many revisits give you a baseline against which to measure changes, and in that data something was off, not in the surface. The surface looked the way the surface always had. The story that began to change came from how Mimas was moving, from a wobble too small to see by eye, but precise enough to start unsettling the picture of a frozen, simple world. Now think about how strange that is. Most surprising findings come with surprising images. A new picture, a new reading, something that looks different from what we're used to. Mimas didn't give us that. Mimas looks now the way it has looked in every clear image we have ever had of it. So the evidence comes from underneath, from the moon's behavior, not its appearance. And that's part of why the case took so long to become a serious one. The surface argued in one direction. Everything you would naturally trust was telling you that this small, scarred moon was finished. The visible answer and the measured answer began to disagree. And of the two, the measured answer turned out to be harder to dismiss. Before any of this became an ocean story, Mimas was already an awkward object. Not in the sense of being mysterious in headlines, in the sense of being a moon that did not quite fit the standard accounting of how heat moves through small icy bodies. Now step back into the system around it. Saturn has a large family of moons. Some are big enough to host atmospheres of their own. Some are tiny shepherds threading between rings. In the inner part of that family, several moons share the same broad neighborhood. Mimas, Enceladus, Tethys, Dione. Each one orbits relatively close to Saturn. Each one feels the pull of the planet strongly. Each one feels the pull of its sibling moons in smaller, repeating ways. So those interactions matter. They are not background detail. They are the engine room of icy moon physics. Here's the basic idea. A moon doesn't orbit a planet on a perfectly circular path. The orbit is slightly stretched. As the moon moves through it, the gravitational pull from the planet rises and falls. The body of the moon, being not quite rigid, stretches and relaxes in response. It bulges, it settles, it bulges again. Each cycle is small. Each cycle releases a little energy as heat inside the moon, and that's tidal heating, one of the most important sources of internal warmth in the outer solar system. Now slow down on the mechanism a moment longer. The flexing is small in any single cycle. We're talking at most about the moon's shape changing by meters as it moves through its orbit, on a body hundreds of kilometers across. The strain is tiny, but it repeats. Each orbit it happens again. Over millions of years, those repeated small flexings add up to a substantial amount of energy delivered to the inside of the body. So the exact amount depends on how rigid or how soft the moon is at different depths, and on how fast the flexing happens compared to how fast the materials can respond. But here's a wrinkle. The same nominal tidal flexing on a fully rigid moon and on a partly soft moon produces wildly different amounts of internal heat. A perfectly rigid object barely heats at all. There's no give. A material that flows too easily also barely heats, because the energy goes into smooth deformation without resistance. The strongest heating happens in materials that are intermediate, stiff enough to resist the deformation, soft enough to give a little, with internal friction that turns the flexing into warmth. So the question of whether Mimas has a warm or rigid interior matters. The answer affects how efficiently the moon converts orbital energy into heat. Different assumptions about the inside lead to different predicted heat budgets. Different heat budgets lead to different conclusions about whether liquid water is sustainable. Now look at how this plays out for Enceladus. Tidal heating is the reason Enceladus is alive. The repeated flexing creates real thermal energy in the interior. That energy keeps liquid water beneath the ice. That liquid water reaches the surface in cracks and feeds the plumes we see in Cassini images. The chain is clean. Tides drive heat. Heat drives liquid water. Water leaves the surface in obvious ways. So if we understand Enceladus, the next question is natural. Why doesn't Mimas behave the same way? Mimas is closer to Saturn than Enceladus. By some measures, it sits in conditions where tidal forcing should be a real factor. Small, yes, but small does not always mean cold inside. Enceladus is small too. The bodies are roughly the same scale. The neighborhood is similar, and here's another factor. Mimas sits in a particular dynamical relationship with Tethys. Their orbital periods are linked in a way that periodically reinforces certain gravitational pulls. Other inner moons of Saturn also nudge Mimas's orbit over long times. These interactions can pump up or damp down the eccentricity, and changes in eccentricity feed directly into the strength of tidal heating. So Mimas's orbit isn't isolated. It's part of a system that has been evolving for a very long time. Parts of that evolution leave their marks on what kind of heat budget the Moon experiences in any given era. But when scientists looked at Mimas, they saw the opposite of Enceladus. No plumes, no cracks like the tiger stripes, no fresh terrain, crater after crater after crater, almost everywhere they looked. And here's the Old Mimas Problem. A moon that sat in conditions where you might expect tidal effects of some kind, behaving as if those effects weren't there at all. Now, the working answer for years was that Mimas's orbit and history simply didn't push it hard enough. The exact eccentricity, the resonances with other moons, the timing of past gravitational interactions, all of it could be combined to make the case. Mimas, by this argument, had ended up in a state where tidal heating, if it ever mattered, no longer mattered enough. So that was a defensible position, but it was also fragile. It depended on getting the orbital history right. It depended on assuming that the inside of Mimas was simple enough that we could read it from the outside, and it depended on the surface being a complete record of what had happened. The longer scientists studied the Moon, the more those assumptions started to feel unsafe. Look at the deeper rule under all of this. Across the solar system, we've learned to read interior activity through surface expression. A young surface tells us about heat. A cracked surface tells us about stress. A plume tells us about water. We trust those signals because, most of the time, they have been right. Most of the time, not all the time. So the deeper question that Mimas was already asking, even before any modern ocean claim, was a question about that rule. What if there are bodies where the surface lags the interior? What if there are bodies where internal change has not yet reached the outside? What if the rule we usually trust quietly breaks for some moons, in some conditions, for some lengths of time? And that's uncomfortable, because if it's true, then surface appearance alone isn't enough to sort active worlds from dead ones. Without that shortcut, we need other kinds of evidence. Slower kinds, indirect kinds, measurements of motion, shape, gravity, orbit, libration, the kind of work that takes years to assemble. So Mimas, sitting there with its perfect-looking dead surface, was already a small warning, not a loud one, not yet a confirmed exception, but a signal that the link between inside and outside was not always as tight as the simple stories implied. Now here's a useful phrase that some planetary scientists have used over the years: the Mimas test. The idea is simple. Any general theory of tidal heating, any theory of how icy moons turn orbital energy into internal warmth, has to handle two cases at once. It has to explain why Enceladus is so obviously alive, and it has to explain why Mimas, on the same general logic, is so obviously not. If a theory explains one and not the other, it's incomplete. So for years that test sat there. Theorists worked around it. Some models could pass, others struggled. The simple story, Mimas is just frozen, end of discussion, kept the Moon at the edge of the conversation rather than at the center of it. But the conversation was already shifting, because the early Cassini data was hinting at things in Mimas's motion that were not quite what a simple frozen moon should give. So two completely separate streams of evidence were starting to point at the same body and give different answers. One stream was the surface. The surface said, a quiet, cratered, dead moon. The other stream was the motion. and the motion was beginning to say, "This moon doesn't move quite the way a quiet, frozen body should." Eventually, those two streams had to be reconciled. But before they were, the field had to take the wobble seriously. That meant trusting a measurement that nobody could see in any image. It meant betting that the data was clean enough to support a real interior conclusion. It meant accepting that, on this particular moon, the surface was not the last word. So the question was no longer simply, is Mimas dead or alive on the inside? The question was, how do we measure the inside of a small icy moon when the outside refuses to tell us anything? The answer, when it came, started with a wobble. Picture Mimas in orbit. It travels around Saturn on a path that takes a little less than a day to complete. As it moves, one face of the moon stays pointed toward the planet. Most large moons in the solar system do this. Earth's moon does this with us. The same face, more or less, every time. But that more or less matters. Now think about what tidally locked actually means in detail. Tidally locked moons don't point perfectly. They tilt, they sway, they turn slightly more or slightly less than a perfectly rigid body would, depending on where they are in their orbit. The motion is small, it's regular, it repeats with each circuit. So that motion has a name, libration. Libration is, at its heart, a wobble in the way a moon points. Not the moon spinning out of control, not the moon flipping over, just the moon nodding very slightly as it moves through the gravitational landscape of its orbit. We see the same libration in our own moon when we measure it carefully. We see it across the solar system in any body that's locked to a parent. Now here's a distinction worth introducing. We separate two kinds of libration when we talk about a tidally locked moon. The first is optical libration, essentially a viewing angle effect. As a moon moves around its orbit at a slightly varying speed and at slightly varying distance, our line of sight relative to the moon shifts. We see a little around the edges. That's what lets us see more than 50% of the moon's surface from Earth over time. It's real, but it isn't a deep statement about the moon itself. And then there's physical libration. That's the wobble in the moon's actual orientation in space. The body genuinely turns slightly more, then slightly less, than a perfectly steady rotation would. The amount of physical libration depends on the internal mass distribution and on how rigid or coupled the layers of the moon are to one another. Physical libration carries information about the inside. For Mimas, the relevant measurement was of the physical libration. The team had to extract that signal from images, separating it from the optical effects of changing geometry. That separation isn't trivial. We have to model the camera's view, the moon's known orbit, and the expected viewing geometry. Then we ask what additional rotational variation has to be present to match the observed shifts of features on the surface. Whatever's left over after the optical part is accounted for is the physical libration. Now think about why the size of that wobble matters. Libration depends on what's inside the moon. A solid, uniform sphere wobbles in a particular way. A sphere with a dense core wobbles differently. A sphere with a fluid layer underneath the surface wobbles differently again. The motion at the outside is sensitive to how mass and rigidity are distributed on the inside. So here's one of the few ways we have to look inside a small icy moon without ever drilling a hole. We measure how the outside moves, and we use physics to ask, what kind of interior would let it move that way? For Mimas, the calculation goes like this. If the moon is a frozen, mostly uniform body, what people sometimes call a hydrostatic solid, the libration should fall within a predictable range. Slightly elongated bodies wobble more than slightly round ones. Bodies with simple density profiles wobble in simple ways. The expected number for Mimas on the frozen solid model was small. The number Cassini measured was larger. Now slow down on what Cassini actually did. In 2014, a team led by Radwan Tajuddin published the result in the journal Science. They used Cassini's imaging data to track features on Mimas's surface, frame by frame, with very high precision. By measuring how those features shifted over time, they pinned down how the moon was actually nodding in its orbit. So the technique behind this is called stereophotogrammetry. The idea is straightforward in principle. If you have multiple images of the same surface from different angles, you can reconstruct three-dimensional positions for features on that surface. A small bump becomes a measurable height. A crater rim becomes a defined location. By tracking those reconstructed features across many images, taken at different times and from different vantage points, you can detect tiny shifts that would be invisible in any single picture. For Mimas, the team used hundreds of Cassini images. They identified control points across the surface. They watched how those control points appeared to move as the moon rotated and orbited. The systematic part of that motion is the libration. The random part is the noise. With enough images, the systematic signal becomes clean enough to compare to model predictions. Now think about what that means in concrete numbers. The libration of Mimas amounts to a deflection of the moon's pointing direction by a small fraction of a degree. On a body 400 kilometers across, that deflection corresponds to surface features shifting by a few hundred meters relative to where a perfectly steady rotation would put them. At Cassini's resolution, a few hundred meters is a measurable amount. Just barely, the signal lives at the edge of what the data can resolve. Pulling it out cleanly required hundreds of images and careful analysis. So the 2014 result wasn't an obvious finding sitting in the data. We had to carefully extract a small signal that earlier work had not been able to pin down precisely. And here's what they found. The libration was about twice the size of what the simplest frozen solid model predicted. Now that wasn't a small disagreement. It was a real signal, a signal that the inside of Mimas was not what the simplest model assumed. But what it didn't do immediately was prove an ocean, so this is where it's easy to skip ahead. A larger than expected wobble sounds like a discovery. It sounds like a headline. The next sentence wants to say, and that means liquid water. It does not mean that, not on its own. Here's what a larger libration tells you. The moon's interior is somehow decoupled from the simplest assumption. That decoupling could come from an ocean, a layer of liquid water that lets the outer ice shell move slightly independently of the deeper interior. But it could also come from other arrangements. A core that's shaped unusually, mass distributed in a way that doesn't match a smooth, relaxed body, internal structure that's more complicated than the model. Each of those would shift the wobble. Each is a real possibility. Cassini's data on its own couldn't distinguish between them, so the 2014 result did something specific. It opened a question. It said, "The inside of Mimas is not as simple as the surface suggests." Beyond that, the data was honest about its limits, and that honesty is part of what made the result trustworthy. The team didn't claim more than they had measured. They listed the possibilities. They explained which ones the data favored and which ones it did not. They left the door open for further work, but notice what had happened. The picture of Mimas had changed without the picture of Mimas changing. The images were the same. The crater map was the same. Herschel had not moved. The surface was still the surface. What had changed was that one extra layer of evidence had been added underneath all of that. The motion, and the motion, measured carefully enough, would not let the simple frozen solid story pass without a question. Now step back and notice something about the way we do this kind of science. When we can't see inside a body directly, we have to triangulate. We use motion, we use shape, we use density, we use orbital behavior. None of these is a photograph, none of these is a sample. Each is an indirect line of evidence, and each only carries weight when it's combined with the others. So for a long time, on Mimas, those indirect lines barely existed. We had a surface, we had a basic mass, we had general orbital information. We didn't have the kind of fine measurement that lets you start guessing about interiors. Cassini changed that. Long mission, careful instruments, repeat passes by Mimas at different angles and distances. The libration result was one of the first products of that work. Not a single observation, a slow accumulation of image data, refined into a measurement that the older images simply could not have produced. So when we ask why the modern ocean case came together when it did, part of the answer is technical. We had to wait for the right kind of data. The surface had been visible for a long time. The motion was new. And once the motion was on the table, the simple story broke. But the libration didn't produce one answer. It produced two. One of those answers said, "There's a layer of liquid water beneath the ice." The other said, "The inside of the moon is shaped unusually, in a way that doesn't require water at all." Both could fit the data. Both deserved a serious hearing. That fork leaves two possibilities, and both have to be taken seriously. The measurement was real. The interpretation was not unique, and that's a sentence worth repeating, because it gets to something honest about how this kind of science works. A measurement is what an instrument records. An interpretation is what we conclude the measurement means. The two aren't the same. A good measurement can be consistent with more than one story about the world. The job of the field is to figure out over time which of those stories does the better work. So after 2014, Mimas had a specific version of this problem. The libration was larger than expected. Two main explanations could account for that fact. One was a global subsurface ocean. The other was a non-hydrostatic core. Both would change the way the outer parts of the moon respond to Saturn's pull. Both would, in principle, leave a similar mark on the wobble. Now take the ocean idea first. Picture Mimas as it would be in the ocean version. Outside, an ice shell, frozen solid, perhaps a few tens of kilometers thick. Below that shell, a layer of liquid water. Below the water, a deeper interior of rock and ice mixed together, sitting at the moon's center. Now think about how the outer shell moves. It's being pulled on by Saturn's gravity. It's locked into the orbit. It nods through libration as the moon goes around. But because the shell is sitting on top of liquid water, it's not rigidly attached to the deeper interior. The water acts as a kind of buffer. The shell can move slightly more freely than a solid moon would allow, so that extra freedom shows up as a larger wobble. The libration grows because the shell, decoupled by the ocean beneath it, responds to gravity with less restraint than a one-piece moon. Here's a useful way to feel this. Imagine two eggs, one hard-boiled and one soft-boiled, spinning on a table. Both look similar from outside. The hard-boiled one moves as a single piece. The soft-boiled one has the shell coupled to a more fluid interior, and it wobbles differently when nudged. The principle is similar, even though the materials and scales are vastly different. Whatever sits between the outer shell of a body and its deeper interior changes how the body responds to motion. A liquid layer is one of the most effective decouplers we know of. So that's the ocean explanation, clean, physically reasonable. It connects motion at the surface to a layer beneath that we cannot see. Now take the alternative. A non-hydrostatic core sounds technical, but the idea isn't complicated. Hydrostatic in this kind of discussion means an interior that has settled into the smooth shape it would naturally take under its own gravity, given enough time. A non-hydrostatic interior is one that hasn't settled into that smooth shape. The mass inside is distributed unevenly. We may have an elongated core. We may have regions of denser or lighter material in places where a simple model wouldn't put them. And here are the real reasons a small moon might have a non-hydrostatic interior. Small bodies have weaker self-gravity than large ones, which means their interiors take longer to relax into smooth shapes. Materials that are colder are stiffer, and stiffer materials hold on to irregularities for longer. A moon that experienced a major impact, like the one that made Herschel, might have had its interior stress field perturbed in ways that didn't fully settle out. A moon that formed from materials of different densities might have ended up with mass distributions that never fully sorted themselves. So none of these scenarios is exotic. All of them are physically plausible for a body the size and temperature of Mimas. If the inside of Mimas is shaped that way, the wobble at the outside changes too. An unevenly distributed mass responds to gravitational pulls differently than a smoothly distributed mass. The libration we'd measure could be larger as a result, even without any liquid water anywhere. So that's the core explanation. It doesn't need an ocean, it just needs the inside to be more complicated than the simplest assumption we'd otherwise make. Both stories could account for the 2014 measurement. Neither one was in obvious conflict with the data. Neither one was obviously stronger than the other on the basis of libration alone. Now here's the kind of moment that often gets compressed in popular accounts. The measurement gets reported, the most striking interpretation gets attached to it, The competing interpretation gets a brief mention, if any, and then disappears. The story moves on as though the question were settled. But it wasn't settled in 2014 on Mimas, and here's why the field has to be careful in cases like this. A measurement that's consistent with multiple interpretations is, in mathematical terms, an underdetermined problem. There are more possible solutions than constraints to pick one out. To resolve it, you need additional measurements that the candidate's solutions disagree on. If both candidates predict the same outcome for some new measurement, that measurement doesn't help. If the candidates predict different outcomes, that measurement becomes a discriminator. So part of what good experimental design does, in this kind of situation, is identify what discriminator measurements would look like. After 2014, several were already on people's minds. A precise gravity measurement during a close flyby. A detailed shape measurement that could distinguish between hydrostatic and non-hydrostatic figures. A long baseline orbital tracking analysis, sensitive to fine structure. The 2024 result was, in essence, the orbital tracking discriminator, the measurement whose outcome the two candidate interpretations would have predicted differently. The non-hydrostatic core option was a real possibility. There were geophysical reasons why a small icy moon might not have fully relaxed into a hydrostatic shape, especially if it had experienced strong impacts like the one that made Herschel, or unusual orbital histories. The interior could have inherited shape information from earlier events. That history could leave fingerprints in the libration. So the field didn't jump straight from libration to ocean. We paused. We listed both options. We made the case that further work was needed. Now think about why Mimas didn't immediately get treated like Enceladus. Because Enceladus had something Mimas didn't. Enceladus had multiple independent lines of evidence pointing the same direction. There were the plumes. There was the hot terrain at the South Pole. There were gravity measurements during close flybys. There were chemistry detections in the plume material itself. Each of those, by itself, would have been suggestive. Together, they made the ocean case very hard to deny. Mimas had one strong libration measurement. An important start. Not the same kind of evidence stack. So the honest position, in the years just after 2014, was that Mimas had become more interesting, not yet conclusive. The interior was not as simple as the surface implied. Beyond that, the field was still working. Here's a pattern that shows up again and again in planetary science. A measurement comes in. It's consistent with multiple physical pictures. The work that follows is not about finding more dramatic data. It's about finding measurements that the different pictures predict differently. If the ocean version says one thing should be true, and the core version says another, then a good follow-up measurement is one that can tell them apart. So for Mimas, a few candidates for that kind of follow-up work were already on people's minds. A closer look at the moon's overall shape. A non-hydrostatic core would produce a specific kind of shape signature, while an ocean-bearing moon would produce a different one. A careful study of the orbit. If the inside of Mimas was reshuffling energy through tidal flexing, that energy had to go somewhere, and the orbit might carry traces of it over long times. But these weren't quick experiments. Cassini was a long-running mission, and its observations of Mimas were limited by the geometry of its tour through the Saturn system. New analyses had to wait for new flybys, or for re-examinations of old data with sharper techniques. Meanwhile, the surface still said dead. So that's part of why the ocean explanation took so long to feel persuasive. Not just that the libration on its own was ambiguous. The visible evidence was pulling in the other direction. A heavily cratered, quiet surface argued for a simple frozen interior. A larger-than-expected wobble argued, gently, for something more complicated. Now think about which side that imbalance favored. The surface had years of habit behind it. The wobble had a single careful study and an open question. Most fields, given that imbalance, default to the older interpretation. Mimas was no exception. The dead moon picture stayed dominant. The interior question stayed open. The ocean idea sat in the background as one of two possibilities, not yet promoted to the leading explanation. But what the 2014 work had done was real. It had broken the simple story. Even if the resolution took years, the previous certainty was gone. Mimas had moved from settled case to open problem. And to make the ocean more than one possible fit to a wobble, we had to ask a harder question. Could a moon this small, this cold, this far from the sun, actually keep liquid water beneath its surface for any meaningful time? If the physics didn't allow it, the ocean answer was a non-starter no matter what the libration said. If the physics did allow it, the case for an ocean would rest on more than geometry. It would rest on whether the moon could plausibly host one in the first place. So that's the next question to take seriously. Now start from the most natural objection. Mimas is small, Mimas is cold. Whatever heat is inside it should leak away into space. And that's not a wrong intuition. It's a useful starting place. Small bodies have a high ratio of surface area to volume, which means they radiate heat more effectively for their size than larger bodies do. They tend to cool faster. They tend to freeze through earlier. Combined with the deep cold of the outer solar system, that should make Mimas a hard place to keep liquid water alive. So why is the question even open? Because the heat doesn't have to come from inside the moon's original formation. It can come from somewhere else entirely, the outside, and specifically it can come from gravity. We've already seen the basic idea. As Mimas orbits Saturn, the planet's pull stretches the moon. The orbit isn't a perfect circle, it's slightly elongated. As Mimas moves around, the strength of Saturn's pull changes. The moon flexes in response. With each cycle, a small amount of orbital energy converts into heat inside the body. That's tidal heating. Now think about what tidal heating depends on. The size of the orbit's eccentricity, the distance from the parent body, the internal structure of the moon, the properties of the materials it's made of, especially whether they deform easily or not. For an ocean to exist beneath Mimas, the right combination of these has to produce enough internal heat to stop a layer of water from freezing solid. But enough heat sounds vague. It isn't. There's a specific balance we need to think about. Heat is going in, generated by tidal flexing. Heat is going out, conducted through the ice shell to the surface and then radiated to space. If the input matches or exceeds the output at the right depth, we can have a layer of water sitting between the cold outer shell and the deeper interior. If the input is too small, the water freezes. If it's too large, the shell may melt through, and we get a much more obvious surface signature. So the interesting case for Mimas is the middle one. Just enough warmth, in just the right place, to keep a layer of water liquid below a thick ice shell. Not enough to crack the surface or punch obvious holes through the ice. Now look at what scientists did with that picture. In 2022, Alyssa Roden and Matt Walker published modeling work that put numbers on it. They asked, under what conditions could Mimas actually host an ocean today? What does the ice shell have to look like? How thick? How warm at the bottom? What kind of tidal heating budget would the moon need? Their conclusion was carefully bounded. Under a range of plausible assumptions, an ocean was physically possible beneath an ice shell roughly 24 to 31 kilometers thick. The shell would have to be warmer at the base than at the surface, which is normal for any thick layer of ice. The heat flux from below would have to fall in a particular range. The tidal dissipation inside the moon would have to do enough work, but not too much. Possible, not proven. The word matters, and what that work did was take the ocean idea out of the realm of pure geometry, where it had been sitting since 2014, and place it in the realm of physics. The ocean was no longer just a way to explain a wobble. It was now a configuration the moon could plausibly be in, under realistic assumptions about ice, tides, and heat. So that's not a small step. Many ideas in planetary science survive at the geometric level for a while. They explain a measurement, but they don't have a clean physical picture behind them. Often, when someone tries to build the physical model in detail, the idea breaks. The ocean version of Mimas didn't break under that kind of test. It survived a serious attempt to model the actual heat budget of the moon. Now slow down on another piece worth understanding. The behavior of ice. Ice isn't a single material. Ice that's very cold, near the surface of an icy moon, is brittle. It cracks. It holds its shape rigidly under most stresses you would apply on short timescales. Ice that's warmer, deeper in a shell, behaves differently. It can flow slowly under stress, like a very stiff fluid. The boundary between brittle and flowing depends on temperature, on how fast the stress is applied, and on the structure of the ice itself. So this matters because the way an ice shell responds to tidal flexing depends on how it deforms. A shell that's mostly cold and brittle dissipates energy in one way. A shell with a warm, slowly flowing lower layer dissipates energy differently. The difference can be the difference between a frozen moon and a moon with a hidden ocean. In Mimas's case, the relevant calculations have to handle this carefully. We have to allow for ice that behaves differently at different depths. We have to track how heat flows through that layered system, and we have to make sure the resulting shell is consistent with what we know about the moon's overall shape and density. Now think about how complicated that calculation actually is. The viscosity of ice varies enormously with temperature. Just below the melting point, ice can flow on timescales of years to thousands of years. A few tens of degrees colder, the same ice is essentially rigid on million-year timescales. Across an ice shell tens of kilometers thick, we traverse this entire range. The bottom is on the warm end, the top is on the cold end, and the middle does whatever the temperature gradient allows. So tidal heating, which depends on how the ice deforms, varies through the shell too. Most of the dissipation happens in the warmer, more deformable layers near the base. The colder, brittle layers above contribute less. The heat generated at the base then flows upward through the shell and eventually radiates to space. The balance between heat generation in the warm layers and heat conduction through the cold layers sets the equilibrium shell thickness. And here's why the answer comes out as a range rather than a single number. Different assumptions about the ice rheology, about how exactly viscosity depends on temperature, about how stress is distributed within grains, about how impurities affect deformation, give somewhat different equilibrium shells. The mid-20s to low 30s of kilometers that Roden and Walker found is the range that's robust across reasonable choices for these inputs. Some particular models prefer the lower end, some the higher, so when Roden and Walker did this, the bounded answer they reached was that a shell in the mid-20s to low 30s of kilometers with a specific kind of thermal profile could sit on top of a liquid water ocean and still be physically self-consistent. And the ocean had become, at minimum, a viable model. Now notice what is and isn't being claimed. The shell thickness number isn't a direct measurement. It's the result of a model that takes physical inputs and asks what shell would be consistent with them. The ocean isn't being seen. It's being shown to be possible. The plausibility is real, but the case still rests on the model being correct. So that's one of the recurring patterns of indirect planetary science. Each new piece of work either tightens or loosens what's allowed. Each new piece either makes the favored interpretation more comfortable or harder to defend. After Roden and Walker, the ocean explanation was more comfortable than it had been. We'd moved from consistent with one measurement to consistent with one measurement and with detailed physical modeling. A different kind of footing, but it was still not a closed case. There was still the alternative, the non-hydrostatic core. There was still the surface argument. There was still the fact that nothing in any image of Mimas had ever shown the kind of surface activity that an ocean would normally suggest. And here's a new problem hiding inside the plausibility result. If the ocean was real and the shell was kept in the conditions the model required, then the shell should have been doing something to the surface for as long as the ocean had existed. Warm shells deform. Warm shells lose sharp topography over time. Not an opinion. That's what ice does over geological time when you keep it warm. So if Mimas had an ocean and the model said the shell was warm enough at the base to keep that ocean alive, then the long crater record on the surface was harder to keep, not easier. And the same physics that made the ocean possible was now in tension with the moon we could see. So that's where the giant crater stops being a thumbnail. Look at Herschel again. The 130-kilometer scar, the high rim, the central peak, the crater that gave Mimas its visual identity in the first place. Herschel is a fact. The crater is preserved. The relief is sharp. Whatever happened to Mimas after the impact that made Herschel did not erase the impact. Now that fact, on its own, used to be the easy conclusion. Mimas is cold and rigid. Of course Herschel is preserved. The ice doesn't flow. The crater stays the way the impact left it. Case closed. But once the ocean idea is on the table, that closed case opens again. Because if Mimas has an ocean, the ice shell above it is in a warm, thermally active state. And a warm shell isn't as rigid as the old picture assumed, not a piece of solid stone in the geophysical sense. It's a layer that can very slowly deform under its own weight and under the stresses placed on it by big features sitting on it. So big features like Herschel. Now think about what happens to large craters on warm or weak surfaces. The technical term for the process is relaxation. A crater is a hole. The ground around the hole is higher than the hole's floor. Gravity pulls everything toward the same level. If the ground is rigid enough, gravity loses. The crater stays as it was, but if the ground is warm enough or weak enough, gravity slowly wins. The word, the fornoftenos, denies its relays. The crater stays as it was, but if the ground is warm enough or weak enough, gravity slowly wins. The walls of the crater sag inward, the floor rises a little, the rim rounds off. Over long enough time, the difference between the crater and the surrounding terrain becomes smaller and smaller. A relaxed crater is one that has been slowly smoothed by the deformation of the body underneath. We see this elsewhere in the solar system. On warmer or weaker icy moons, large craters often look softened. Their relief is muted, their rims are low. The surface tells you, without needing any other measurement, that the body has spent significant time in a state where ice could deform. Now think about how the timescale for relaxation actually scales. The rate at which a crater relaxes depends on how warm the underlying ice is, on the size of the crater, and on the gravity of the body. Larger craters on warmer bodies, with stronger gravity, relax faster. Smaller craters on cold bodies barely relax at all on any geological timescale we'd notice. Herschel is large. The gravity at Mimas is small. Whether the basin would have relaxed visibly depends sensitively on how warm the shell beneath it has been, and for how long. So model calculations of crater relaxation on Mimas, under different shell temperature assumptions, give different answers. A shell that has been warm at the base for hundreds of millions of years would have softened Herschel substantially. A shell that has been warm at the base for a few million years would not have. The exact threshold depends on the choices in the model, but the broad shape of the answer is robust. But Herschel doesn't look like that. Herschel looks like a fresh wound on a hard moon. The relief is preserved. The rim is high. The central peak is intact. By every visual measure we have, this crater hasn't had a chance to relax much. Now we have a tension. If Mimas's ocean has been there a long time, and the shell has been in the warm base state the models prefer, then Herschel should have been quietly deforming. The fact that Herschel still looks the way it does puts a constraint on how long that warm shell state can have lasted. So here's what it means to use Herschel as a clock. Not as a stopwatch, not as an exact timer that says here is the date, but as a constraint on the moon's thermal history. Whatever happened on the inside, the shell could not have been in the deformation-friendly mode for so long that it would have erased the basin we see, and that's a real constraint. It limits the kind of histories that are allowed. Now notice how this twists the ocean argument in a useful way. The ocean idea, taken at face value, sits comfortably with a long-lived warm shell, but a long-lived warm shell does not sit comfortably with a sharply preserved Herschel. So either the ocean has not been there for very long, or the shell has been doing something more complicated than the simplest version of the model assumes, or something else is going on. The cleanest of those options, the one the field has tended to find most attractive, is the first. The ocean is geologically young. Not young in the sense of recent in human terms. We're still talking about millions of years, possibly tens of millions, in different versions of the analysis. Young here means short compared to the age of the moon, and short compared to the age of the cratered surface we see. Now picture how the timeline would actually work if the ocean is young. Most of the moon's history was spent in the frozen-through state that the surface seems to record. The cratered face built up over the long, quiet period. Then, relatively recently in geological terms, conditions changed. Heat began to build up inside. Ice near the deeper interior began to melt. A layer of water formed beneath the shell. The shell, during this newer phase, may have warmed at its base, but not for long enough yet to relax Herschel. So that's the version of the story that many of the recent analyses lean toward. Not because the model demands it directly, but because it's the cleanest way to handle the surface evidence and the interior evidence at the same time. But here's a piece of caution to add. The exact case that Herschel proves the ocean is young is still being refined. The argument depends on how we model relaxation, on how we estimate Herschel's age from cratering statistics, and on the detailed thermal behavior of the shell. Different choices in each of these can shift the answer. The general direction is robust. The precise numbers are not as locked. And what's robust is the structure of the argument. Surfaces preserve a record. Warm interiors erase records. If the surface is heavily preserved and the interior is warm, then the warmth is recent. A sequence we can apply to many bodies, not just Mimas. So worth saying clearly, Herschel doesn't prove an ocean exists. It doesn't on its own prove the ocean is young. What it does is give us a constraint on what kind of ocean history is allowed if there is one. It rules out, in effect, the comfortable picture of a Mimas that has been quietly hosting an ocean for billions of years under a shell that didn't change much. That picture is hard to keep. The crater record argues against it. So the ocean case, if you're going to take it seriously, has to thread a needle. The ocean has to be there. The shell has to be in conditions that allow it. The shell can't have been in those conditions for long enough to erase the visible craters, because the visible craters are, plainly, still there. And here's something quietly elegant about that. The same crater that makes the thumbnail of this moon work is now doing real geological work for the question of when the ocean formed. The most visually distinctive feature of Mimas, the thing that makes you look at it twice, is also the feature that constrains the timing of its hidden interior. The Death Star face, which has nothing to do with the ocean argument scientifically, ends up in the middle of it, because preservation of relief is exactly the kind of evidence that talks to the warmth and weakness of the shell beneath. So the problem isn't just that Mimas may have an ocean, the problem is that it still looks like it should not. And that still is the part the surface evidence keeps pushing on. The motion said, something is different inside. The physics said, an ocean is plausible. The crater said, the warm phase, if there is one, hasn't been around for long. Now each of those, taken alone, would be a moderate claim. Combined, they start to look like a coherent picture of a moon that has changed in ways the surface has not yet caught up with. But the surface was now pushing the ocean into a timing problem. The next big shift came from the orbit. The orbit of a moon isn't just a path. It carries information. And this is one of the more underappreciated facts about how we study the outer solar system. From far away, with no spacecraft inside the body, with no plume to sample, the most powerful tool we sometimes have is precise position tracking. Where a moon is, exactly, at different times. The position of the moon, measured carefully enough across enough years, tells us how it's moving. How it's moving tells us how forces have been acting on it. Which forces have been acting on it tells us, in turn, about the body itself and about the system it's embedded in. So let's talk about astrometry. It sounds dry. It produces some of the most powerful constraints we have. Cassini, during its long stay at Saturn, did a great deal of this work on the inner moons. It tracked their positions against the background stars. It refined the shapes of their orbits to higher precision than any earlier mission could. It built up a long, careful time series of where each moon had been, and Mimas, of course, was part of that work. Now look at how the orbit actually behaves. The orbit of Mimas, like most moons, isn't a fixed ellipse. It evolves. The point of closest approach to Saturn, called the periapsis, drifts gradually around the orbit over time. The eccentricity changes very slightly. The semi-major axis can change too, if energy is being added or removed from the system. These changes are small, well below what you'd notice in any normal observation. But with long enough tracking and careful enough modeling, they become visible. And here's what makes periapsis drift especially informative. The rate at which the periapsis precesses depends on the gravitational field of the planet, on perturbations from other moons, and crucially, on how mass is distributed within the moon itself. A moon with a different interior structure precesses at a different rate, so measuring the precession rate with high enough precision over a long enough baseline becomes a way to constrain the interior. For Mimas, Cassini's tracking baseline was long enough, and the data precise enough, to measure the precession at a level where different interior models predict noticeably different rates. The observed precession was the data point that, when run through the analysis, picked out the ocean version as the best fit. So in 2024, a team led by Valeri Laini published a paper in the journal Nature on the orbital evolution of Mimas, using exactly this kind of long-term Cassini astrometry. The question they asked was simple to state. Given Mimas's orbit and how it has changed during the years we've been able to track it precisely, what kind of interior is most consistent with that motion? And the answer was specific. The data fit best with a global subsurface ocean beneath an ice shell about 20 to 30 kilometers thick, the same general range that the earlier modeling work had identified. Now, however, it was being supported not just by libration and physical plausibility, but by orbital dynamics as well. So this is the moment in the story where the ocean case shifts from one good possibility to leading interpretation. Now think about how the different lines of evidence stack together. The libration measurement on its own was suggestive. It told us the inside wasn't as simple as the surface implied. It allowed both the ocean explanation and the strange core explanation. By itself, it wasn't enough, but the physical modeling work showed that an ocean wasn't just geometrically convenient. It was a configuration the moon could plausibly be in, under realistic assumptions about heat and ice, that moved the ocean from possible to physically reasonable. So the orbital dynamics result then asked a different question. Forget the libration for a moment. Forget the surface. Just look at how the moon's orbit has been evolving. What kind of interior best explains that evolution? And the answer, when the analysis was done carefully, matched the ocean version. The non-hydrostatic core option, which was a strong competitor on libration alone, didn't produce as clean a fit when the orbital evolution was included. The ocean version did. Now here's what scientists mean when they talk about evidence converging. Different kinds of measurements, taken with different methods, addressing different aspects of the same body, all pointing at a similar interpretation. Each measurement on its own would be open to question. Together they make alternative explanations harder to defend. Here's a useful way to put it. Cassini didn't show us water directly. It showed us a moon whose motion is hard to explain without something hidden below. So that distinction is the key point, worth slowing down on. We're not at the point where someone has dropped a probe into Mimas's ocean and reported what they found. We're not at the point where a plume has been sampled and the ions counted. Those would be direct detections, and they're not what we have here. But what we have instead is a fine-grained picture of a moon's behavior that is best fit, by current models, with an interior that includes a global ocean. The ocean is inferred from how the moon nods, how its orbit drifts, and how those motions would propagate through different kinds of internal structures. So that's a different kind of evidence. Not weaker because it's indirect, only weaker if you mistake it for something it isn't. As long as we remember that it's the result of a careful model fit to long-term observations, it's exactly as strong as the underlying analysis allows. Now here's a useful analogy from Earth science. We don't look at the inside of the Earth directly. We look at how earthquakes travel through it. The seismic waves bend, slow, speed up, and reflect in ways that depend on what they're passing through. We use those wave behaviors to construct a picture of the deep interior. There's no photograph of the core, there's a model of the core, fit to a great deal of indirect evidence. The Mimas case is similar in spirit, even though the methods are very different. The orbit and libration are the equivalents, in this analogy, of seismic signals. They carry information about the inside of the moon out to where we can measure it. We don't see the ocean, we see the consequences of the ocean on the way the moon moves. And here's where it becomes important to keep the language honest. After Laini 2024, careful summaries say things like, The orbital evolution of Mimas is best explained by a subsurface ocean. They don't say an ocean has been detected on Mimas in the same direct way as Enceladus. Different statements. The Enceladus case has both indirect modeling and direct sampling backing it. The Mimas case has indirect modeling backing it, with a now stronger, multi-strand version of that modeling than before. So the shell thickness of about 20 to 30 kilometers is also a model output. It's the range that best fits the combined data, not something that has been directly imaged. The same caution applies here as it does to the libration result. The number is meaningful, but it inherits its meaning from the model, not from a direct observation. Now, what did the 2024 result actually change? It changed the strength of the inference. Before it, you could honestly look at the ocean idea and say, this is one of two reasonable interpretations of the libration data. After it, you have to say, this is the interpretation that best fits the libration data, the physical plausibility constraints, and the orbital evolution measurements, all at the same time. So that's a different thing to say, and a thing that's much harder to walk away from. But notice that the surface hasn't budged through any of this. Herschel still looks the way Herschel has always looked. The cratered shell is still cratered. Mimas, as an object you can photograph, hasn't changed at all. What has changed is the weight of the inferences we can make about what's inside it. So that gap between what the surface seems to say and what the deeper measurements imply is now wider than it has ever been. The interior story is louder. The exterior story is the same as it always was. Both are about the same moon. Both have to be true at once. Now, how can both be true at once? That's the question that has been waiting underneath everything so far. The libration opens it. The physics widens it. The orbit deepens it. But the stronger the ocean case becomes, the sharper the surface problem becomes. Ocean worlds usually leave clues. That's the working assumption. When liquid water sits beneath an ice shell on a small body in the outer solar system, the shell tends to record that fact in some way you can see from above. Cracks, fractures, resurfaced terrain where ice has cycled out from below, plumes of vapor and ice grains escaping through openings in the shell, localized hot regions where the shell is thinner and more active, streaks of fresh material that catch the sun differently from the older terrain around them. So we've learned to look for these things. Enceladus has them. Europa around Jupiter has them in a different style, the bigger Galilean moons in different ways. Titan has its own surface processes. The pattern broadly is that internally active worlds tend to advertise that activity through their faces. And here's part of why Mimas was an unlikely ocean candidate for so long. It does none of those things in any obvious way. Now look at what Cassini's imaging campaigns actually found. They covered Mimas in considerable detail. They showed the moon at high resolution. They mapped craters of various sizes across the surface. They looked for signs of activity. What they found was a moon that looked, on every viewable scale, like a quiet, ancient ball of ice. So no Enceladus-style tiger stripes on Mimas. Nothing that looks like the long parallel cracks at the south pole of Enceladus, where warm material reaches the surface. No obvious plumes leaving the moon, despite Cassini specifically looking for any sign of escaping vapor. And no obvious global fracture pattern of the kind you might expect if a sustained ocean had been pushing on the shell from below. No large-scale resurfaced regions where younger material has filled in old terrain. The crater record is dense. The crater record is preserved. The crater record is, in most places, undisturbed. So if you're trying to argue that Mimas has an ocean, that's the strongest objection you have to face. Now look at the objection carefully. It isn't that some scientists prefer the dead moon picture for sentimental reasons. The objection is that, across the bodies we've been able to study, surface expression has been one of our most reliable signals of internal activity. If you have an ocean, you usually leave a trace. Mimas does not leave that trace, at least not in the obvious styles. So this deserves to be felt, not enough to mention it as a small caveat and move on. It's the central problem the ocean case has to handle, and it's a problem that's genuinely hard, and here are the responses to it. The first is to question whether all ocean worlds must look alike. Just because Enceladus is loud doesn't mean every body with an ocean has to be loud. Different sizes, different orbital histories, different ice properties, different ocean depths might all give very different surface signatures. Ocean worlds may vary across a spectrum. Some of them may sit much closer to the quiet end than the obviously active end. So that's a reasonable point, also by itself a little unsatisfying. Saying that ocean worlds can look different isn't the same as saying that one specifically should look exactly like Mimas. A theory that allows everything explains nothing. The second response is to recognize that the surface always lags the interior. A change inside an icy moon doesn't propagate to the outside instantly. There's time scale involved. Heat takes time to move through a thick ice shell. Stress takes time to build up. Cracks take time to form. Plumes require not only an ocean but also a path to the surface, and that path may take a long time to develop, so if the ocean is recent, the shell may simply not have had enough time to express it. The fractures might be coming, but not yet. The activity might be building, but not yet visible. The moon could be early in a transition. The outside, in this view, is a record of the long, quiet period before the interior changed. It hasn't yet been overwritten. Now here's the core idea behind the young ocean reading. The response works only if the ocean really is geologically young. It doesn't work for an ocean that has been around for 1 billion years. It works for one that has been around for tens of millions. The third response is more cautious. We have to admit that the surface is a real piece of evidence pointing one way. The motion is a real piece of evidence pointing the other way. The field has to keep both in view at the same time. The surface doesn't vanish because we now have orbital data. The orbital data doesn't vanish because the surface looks dead. Both stand. The interpretation that wins in the long run will be the one that handles both better than its rivals. So that third response is the most honest one in the short term. It doesn't pretend the objection has been resolved. It just refuses to let either side dismiss the other. But here's one more thing to say about surface evidence. We have to be careful not to assume that no obvious signature means no signature at all. The Cassini imaging is detailed, but it isn't perfect. Subtle, slow, distributed deformation across a heavily cratered shell can be hard to detect, especially if it hasn't progressed far. Small fractures or zones of subdued relief, or patches where the texture changes in a low contrast way, can be missed in standard analysis. Future work, or future missions with new instruments, may find features in Mimas's shell that we haven't yet noticed. So that's not the same as saying there must be hidden activity. It's saying that no clearly identified surface signature so far, and the surface is definitively unmodified, aren't the same statement. Now think about what kind of feature we'd actually be looking for if the young ocean reading is right. If the ocean has only been there for a few million years, the shell may have begun to develop subtle stress patterns at its base, places where the warm interior is starting to push on the cold outer layers. These patterns wouldn't appear as obvious tiger stripes. They might show up as small fractures, distributed irregularly, or as zones where the surface has shifted by tens of meters relative to the surrounding terrain. Hard to detect in standard imagery, possibly visible with high-resolution stereo work, or with surface altimetry data. So the absence of obvious large-scale activity doesn't fully exclude the possibility of subtle, recently emerging features. We may, with better data, find that Mimas is showing the first faint signs of the transition we'd expect from a young ocean picture. Or we may find nothing, in which case the young ocean reading would have to explain why a few million-year-old ocean has produced no detectable surface response at all. Either result is informative. The current state, no obvious signs, no detailed search yet, sits between those two possibilities. And even at its mildest, the surface objection is strong. The most striking surface features on Mimas are the craters. The crater record dominates everything you see. If there's an ocean below it all, the shell has somehow held its old shape across most of the body for most of geological time, and any modifications it has experienced are far less obvious than they are on Enceladus or Europa, so that's a real situation. Not one we can wave away. Now here's where that leaves us. The interior measurements, when you trace them carefully, point toward an ocean. The exterior measurements, when you look at them in the usual way, point toward a long frozen moon. Both are about the same body, both are, at the level of the data, reasonable. So if we're going to take the ocean case seriously, we can't simply say the interior story is right and the exterior story is wrong. We have to find a version of events in which both can be true at once, a version in which a moon can carry a heavily preserved crater record on the outside while hosting a global liquid water layer on the inside. The leading answer isn't that the surface means nothing. It's that the ocean may be too young for the surface to have fully responded. Every clue has to pass through the same contradiction: old surface, young interior. That contradiction now has to be reconciled. An ancient-looking surface and a recent interior change can coexist for a time. That's the central idea. Keep it in mind, because everything depends on it. Now think about the two faces of the moon side by side. The surface of Mimas is, by every measure available to us, old. The crater record is dense and preserved. The big basin at Herschel still looks fresh in geological terms. There are no obvious zones of younger terrain. As an object photographed from the outside, Mimas wears a long, undisturbed history on its face. But the interior of Mimas, by every measurement we've been able to make from the outside in, is no longer simple. The libration is too large for a frozen solid model. The orbital evolution is best fit by a global ocean. The physical modeling shows that such an ocean is plausible under realistic assumptions about ice and heat. So the problem is fitting these two facts onto the same moon. And the cleanest available story is that the ocean is geologically young. Now, what does young mean here? Young on this scale means short compared to the age of the surface. Young doesn't mean centuries. It doesn't mean human time at all. It means roughly tens of millions of years, give or take. There are different framings of this in the literature. One, summarized in materials from the Institut de Mécanique Céleste et de Calcul des Éphémérides, gives an age of about 5 to 15 million years. Another, more conservative framing in news coverage of the same general work, talks about within roughly 25 million years. Not exactly the same number. Different ways of summarizing what the modeling allows. So important not to flatten these differences. 5 to 15 million years and within 25 million years overlap, but they reflect different choices about how to report uncertainty. The lower number tends to come from specific best fit values. The higher number tends to come from the upper end of what the modeling cannot rule out. Both are modeled, not measured. Neither is a directly dated event, but what unites them is the order of magnitude. Whether you take the tighter or the looser version, we're talking about a feature of the moon that's far younger than the surface around it. The surface records billions of years of quiet existence. The ocean in this picture records something that may be only a tiny slice of that history. Now a question presses immediately. Why would an ocean only have formed recently? What changed? The proposed answer involves the orbit, so picture the system. Mimas is part of a gravitationally interacting set of moons. Saturn pulls on it. Other moons pull on it more weakly. Over time, the moon's orbit can shift in eccentricity and shape because of these interactions. Resonances with other moons can drive the eccentricity up. Eccentricity, remember, is what keeps tidal flexing strong. A more eccentric orbit means the moon is being squeezed and released more strongly across each cycle. More squeezing means more tidal heating. So the picture in simplified form goes like this. Mimas spent most of its existence in a state where the eccentricity was low enough that internal tidal heating was modest. The interior stayed cold. The shell stayed frozen. Whatever heat was in the moon mostly leaked away, and the surface accumulated a long record of impacts. Then, at some point, the orbit changed. The eccentricity rose. Tidal flexing increased. Heat began to build up inside the moon at a faster rate than it could be lost. The interior, especially at depth, warmed. Ice began to melt. A layer of liquid water formed. The shell above it, perhaps several tens of kilometers thick, gradually warmed at its base, but remained frozen and rigid through most of its thickness. And this happened, in the model timeline, only a handful of millions of years ago. From the moon's point of view, a recent event. Now think about how short that is in cosmic terms. Mimas itself is about 4 billion years old. Its surface, accumulating craters, has been there for something like that entire span. A few million years is 1 part in 1,000 of the Moon's life. If we map Mimas's history onto a single human year, a 5 million year ocean would have appeared sometime in the last few hours of that year. The surface, on the same scale, accumulated its craters across the previous 12 months. So we're, in this picture, watching Mimas in the last hours of a year-long history. The interior has just changed. The surface still records the long quiet that came before. Both are present at once, but they belong to different eras of the Moon's life, and there's something dizzying about that framing. We tend to assume when we look at a planetary body that what we're seeing reflects roughly what the body has been doing for a long time. The surface seems to be a stable readout of the body's character. But Mimas is showing us that the readout can lag the underlying state by a substantial fraction of geological time. We may, looking at any given moon, be reading a record from a previous era rather than a description of the present. Now, if that's roughly correct, several things follow naturally. The first is the resolution of the surface objection. The shell hasn't had enough time to develop the kind of obvious features we see on Enceladus. Long fracture systems, large-scale resurfacing, persistent plumes, these would all require sustained activity over much longer periods than the proposed lifetime of the ocean. A few million years, in geological terms, is a small window, not long enough to leave the kind of fingerprint that older active worlds carry. The second is consistency with the Herschel constraint. The shell may be warm at its base now, but it hasn't been in that state for long. Crater relaxation is a slow process. A shell that has had only a few million years to deform isn't going to erase a 130-kilometer basin. Herschel, in the young ocean picture, was already old before the ocean ever formed. It carried over from the cold era, and the warm era hasn't been long enough to soften it noticeably. The third is consistency with the libration and orbital data. Both of these respond to the present-day interior, not to the Moon's deeper history. The libration tells us about how the inside is arranged right now. The orbital evolution that Laney 2024 used is also fairly recent, on geological scales. Both carry the signature of an interior that has only recently become structured the way it is. So put it all together, and you get a coherent narrative. Mimas spent most of its life as the quiet, frozen moon its surface still suggests. Sometime in the recent geological past, something, likely changes in orbital dynamics within the Saturn system, pushed it into a state where tidal heating became strong enough to maintain liquid water beneath the ice. The ocean formed. The shell warmed at depth. The motion of the moon, sensitive to internal structure, began to register the change. The orbit, sensitive to where energy is being dissipated, began to evolve in ways that fit the ocean version. The surface, slow to respond, hasn't yet caught up. Now that story does a lot of work. It handles the surface evidence and the interior evidence with the same set of moves. It doesn't require dismissing either one. It doesn't require Enceladus-like features to appear where none have been observed. It doesn't require the cratered shell to be ignored, but it does require taking seriously the idea that we're looking at Mimas at a particular moment in its history. Earlier, the moon would have looked the way the surface still does, all the way through. Later, if the ocean persists, the surface may eventually start to show signs of the change. Right now, in this view, we're catching the moon mid-transition. The outside is the past. The inside is the present. So if the ocean is young, the surface may be a record of what Mimas used to be, not everything it is becoming. That's what the young ocean reading, taken seriously, is asking us to consider, and we shouldn't pretend this story is final. It's the cleanest reconciliation of the available evidence, but several pieces of it are themselves model results. The age range is modeled. The shell behavior is modeled. The exact orbital history that drove the eccentricity up is, in many published versions, traced through specific scenarios that have their own assumptions. New work may sharpen any of these, future work may push them in new directions. So what the young ocean reading does is offer the most complete version of how can these two stories be true at once that the field currently has. It doesn't collapse the contradiction, it explains why the contradiction is what we're seeing. Here's something quietly important about this kind of explanation. It doesn't eliminate uncertainty, it locates it. It says, the strongest layer is the present-day evidence. the libration, the orbit. The more provisional layer is the timeline. The most provisional layer is the exact orbital scenario that produced the heating. Each layer of the explanation has its own confidence level, and those confidence levels don't all match. So that's honest, and it's the right way to leave the question. The young ocean answer is powerful, also conditional. We're, in effect, betting on a particular slice of cosmic timing, that a moon spent most of its life in one mode and recently switched into another, and that we happen to be living during the switch, and that bet is the price of the cleanest reconciliation. The alternative is to leave the contradiction unresolved. Now this is a good place to pause and sort the evidence. Any account of a hidden ocean can drift easily into talking as though the ocean is a settled fact. It isn't a settled fact. It's a very strong inference. The difference between those two things matters, and it's worth being clear about it before the conclusion. So let's be clear. What's measured? We've measured Mimas's surface in detail. We have its diameter, roughly 394 kilometers. We have the size of Herschel crater, roughly 130 kilometers across. We have a large set of high-resolution images that record the cratered terrain, the rim of Herschel, the central peak, the smaller features distributed across the moon. We have the basic density of Mimas, derived from how it moves and how its gravity affects nearby objects. We have the orbit traced over Cassini's many years at Saturn. We have the libration, the small regular wobble in how the moon points, measured to a precision that earlier work could not reach. And we have the orbital evolution, the slow drift in the periapsis and other parameters, recorded across the years of careful tracking. So these are the things that come, more or less directly, from instruments. Not without analysis. Even an image of a crater requires processing, and even a measured wobble requires careful interpretation of frame-to-frame data. But these quantities are close to the data. They are what we've actually observed about Mimas. Now, what's inferred? The existence of a global subsurface ocean is inferred. We haven't seen it. We haven't sampled anything from it. We haven't directly imaged the boundary between ice and water. The ocean is the configuration of the moon's interior that best fits the libration and the orbital evolution when we plug different interior models into the equations and ask which one matches. So the thickness of the ice shell, around 20 to 30 kilometers, is inferred, a model output. The range of shells that work with the data and with the physics of ice and heat given specific assumptions. Different assumptions give somewhat different ranges, and the age of the ocean is inferred. The framings of about 5 to 15 million years, or within roughly 25 million years, are the result of modeling the moon's thermal and orbital history. They aren't dates that have been read off a sample. They're estimates of when the moon's interior is most likely to have entered its current state, given the amount of internal warmth required, and how fast it could plausibly have built up. The exact orbital scenario that drove the eccentricity up, leading to the proposed heating, is also inferred, often through specific models that involve interactions with other moons. Different orbital histories can produce different heating timelines. The published versions are best fit scenarios, not unique solutions. Now here's the important thing. These categories aren't labeled trustworthy and untrustworthy. Inferred doesn't mean weak. Inferred means we're reading the evidence through a framework of physics and modeling, instead of looking at it directly with our eyes or our instruments. And a great deal of what we know about the universe is inferred in exactly this way. The composition of stars is inferred from how they emit light. The structure of the deep Earth is inferred from how earthquake waves move through it. The masses of distant planets are inferred from how they affect the motion of their host stars. None of those things are directly observed. All of them are taken seriously because the inferences are anchored in measurements we trust and in physics that has been tested, and the Mimas case lives in that same world. Not as direct as a plume sample, not as remote as a guess, sitting in the middle where most planetary science about hidden interiors has to live. Now think about why this kind of inference can become as reliable as direct observation. The strength comes from the chain of physics. Each step in the chain, from observed motion to libration parameters, from libration to interior models, from interior models to ocean configurations, is grounded in well-tested principles. The chain has weak links if any single step rests on shaky physics. The Mimas chain doesn't. The mechanics of forced libration are well understood. The physics of ice rheology is well studied. The dynamics of orbits around oblate planets are part of the standard machinery of celestial mechanics, so when each link is solid, the chain as a whole carries weight. The inferred ocean isn't a wild leap. It's the result of running real physics through real measurements and asking what configuration of the moon's interior is consistent with the observations. But worth remembering that the ocean isn't the only interpretation that has ever been on the table. The strongest named alternative is the non-hydrostatic core. The idea that Mimas's interior is shaped unusually, with mass distributed in ways that mimic some of the same external behavior that an ocean would produce, a serious option after the 2014 libration result, the cleanest competitor to the ocean explanation in the published literature. So why does the field now lean toward the ocean? Because the orbital dynamics result added a constraint that the core option struggles with. A non-hydrostatic core can do interesting things to a libration. It doesn't, in the modeling, fit the long-term orbital evolution as cleanly as a global ocean does. It's easier to construct a core variant that matches one of the measurements than one that matches both, so that isn't the same as saying the core option has been ruled out forever. It's harder to defend now than it was before. New work could change that. A new model, a new piece of analysis, a new measurement could shift the balance again. The ocean is the leading interpretation, not the sole survivor, and here's some humility worth holding about the modeling itself. The ocean version of Mimas isn't a single model, it's a family of models. They share the basic structure, a global liquid layer beneath an ice shell of a few tens of kilometers, but they differ in details. Some have warmer ocean bases, some have cooler. Some have specific shell rheologies, others use different ones. Some treat the moon as relatively recent in its current state, others treat it as a longer-running situation. Within that family, the data picks out a region. The exact best fit is a moving target. So when you hear someone say Mimas has an ocean, what they mean, when they're being careful, is something like this. Among all the interior arrangements we can plausibly model, the one that best fits the libration, the orbital evolution, the surface, and the physics is one that includes a global liquid water layer of a specific approximate thickness, at a specific approximate depth, formed in geologically recent time. And that's a richer claim than we found water. Also, in many ways, a more interesting one. The honest answer isn't weak, it's simply indirect. The evidence points inward through motion, shape, and orbit, instead of through a direct image of liquid. As long as we keep the language disciplined, measured here, inferred there, modeled there, the picture is robust. Now here's one more thing. Some people will hear all of this and feel disappointed. The ocean isn't directly seen. The age isn't directly dated. The exact orbital history is one of several possibilities. They may want a cleaner answer. They may want a sentence that says, simply, Mimas has a 5 million-year-old ocean under a 28-kilometer shell. But that sentence doesn't exist, not at the level of evidence. The reality is more layered. It includes the strong base of measurement and the more provisional layers of inference built on top. To live in this version of the story is to live with that structure. And the structure isn't a weakness. It's what allows us to update the picture as new work arrives. It's what allows us to know which parts to revise if a new measurement contradicts a current claim. The difference between a story that's fragile and a story that's alive in the way frontier science usually is. So once the evidence is separated from the inference, the old dead moon picture no longer survives unchanged. The motion is real, the orbital evolution is real, the physical plausibility is real, the crater record is real, and it constrains the timing. None of these need to be abandoned. They have to be held together, with discipline, in a single coherent reading. Now here's one more point worth making before we move on. Mimas is a case where the surface and the interior tell different stories. Most of our experience with ocean worlds involves bodies where the evidence stacks cleanly, where the direct evidence confirms the indirect, or where the indirect evidence is backed up by visible surface expression. Enceladus gives us both. With Mimas, we are relying more heavily on the indirect chain than we've had to before. That's not a reason to distrust the answer. but it is a reason to stay precise about what the answer actually is. The chain is strong. The chain is not as short as we'd like, and the distinction between what we've measured and what we've modeled is the clearest way to say exactly how strong it is and where the remaining uncertainty lives. If you put the pieces in order, the picture comes together like this. Now look at the surface first. Mimas has a surface that, by every visible measure, looks ancient and frozen. The crater record is preserved. Herschel still looks sharp. There are no plumes, no obvious tiger stripes, no fresh terrain. So Cassini measured the moon's libration and found that it nods in its orbit by a larger amount than a simple frozen solid model would predict. That measurement could be explained by either a global subsurface ocean or a non-hydrostatic core, and detailed physical modeling has shown that an ocean beneath an ice shell, roughly 20 to 30 kilometers thick, is plausible under realistic assumptions about tidal heating, shell behavior, and ice rheology. The ocean isn't a magical configuration, it's one the physics allows. But Herschel places a constraint on how long the moon could have been in a warm shell state. The basin still looks sharp. A long-lived warm phase would have begun to relax it. The shell, if it is now warm at the base, hasn't been in that condition for very long, so in 2024, careful tracking of Mimas's orbit over Cassini's tour revealed an evolution best fit by a global subsurface ocean. The earlier libration result, on its own, could be explained two ways. The combined evidence is harder to handle with the core alternative. The ocean version fits both, and the biggest objection, that the surface shows no obvious signs of an ocean, finds its cleanest answer in the proposed age. If the ocean is geologically young, on the order of a few million to a few tens of millions of years old, the shell hasn't had enough time to develop large-scale features. The cratered face is a record of the long, quiet period that came before. The interior change is recent enough not to be loudly written on the outside yet. So the strongest current reading then is something like this. Mimas probably hosts a global subsurface ocean beneath an ice shell on the order of a few tens of kilometers thick. The most coherent way to square that ocean with the cratered surface is that the ocean is geologically young. The exact age is uncertain, with different framings giving roughly 5 to 15 million years on the tighter side, and within roughly 25 million years on a more conservative side. The shell thickness and the timing both come from models, not from direct measurements. Now that's the picture the evidence supports. Not a sensational picture, a cautious, layered, multi-source picture. And that's part of what makes it strong, so compare it to the picture we had before. Before all of this, Mimas was a small icy moon presumed to be frozen through, a good test case for tidal heating models, because of how its surface differed from Enceladus' surface. An interesting object for studies of impact history because of Herschel. Not, in any serious sense, a candidate for hosting liquid water, and that picture can't be defended anymore. Not because someone wants Mimas to be more interesting. Because the data has piled up in a direction that the older picture cannot absorb. The libration is too large. The orbit evolves in a way that fits an ocean better than a complicated core. The physical modeling shows the ocean can survive. The cratered surface is now a constraint on the ocean's age, rather than a refutation of the ocean's existence. No, the replacement picture is more complicated, but the complication is honest. Mimas isn't just frozen, it's also very probably not obviously alive in the Enceladus sense. It sits in a less familiar category, a moon that has changed in ways the surface doesn't yet show. Now here's a useful category to have. Up until now, our standard playbook for icy moons has tended to sort them into two boxes. The active ones, with cracks and plumes and fresh terrain. The dead ones, with old surfaces and no obvious internal life. Mimas is increasingly evidence that those two boxes don't exhaust the possibilities. So a third category seems to be making itself visible. A moon in transition. A moon whose interior has begun to change but whose surface still mostly belongs to the previous era. A moon where if you only had the photograph you'd file it under dead, but where if you had the motion you'd have to file it under complicated. And to settle this, the field would like more direct measurements of the ocean's depth and thickness. Better gravity data, closer flybys of Mimas with new instruments, spacecraft that could sample any subtle activity that may eventually be found. Long-term tracking of the orbit, continuing past Cassini to refine the orbital evolution. Now think about which of these would be most decisive. Direct gravity measurements during a close flyby would be powerful. By tracking how the Moon's gravitational field affects a passing spacecraft, we can map the interior mass distribution at higher resolution than orbital tracking allows. A non-hydrostatic core and a global ocean produce different gravity signatures. A few targeted flybys would, in principle, be able to distinguish them. Surface ice-penetrating radar would be even more direct. If a future spacecraft carried radar capable of probing through tens of kilometers of ice, it could in principle detect the ocean directly, a sharp boundary in dielectric properties between ice and water. That kind of instrument has been deployed on Mars and is planned for future Europa missions. Adapting it for Mimas would require a dedicated mission, but the technology exists, so the path from leading interpretation to directly confirmed is technically clear. It just requires resources, time, and a successful mission proposal. None of those are guaranteed. But we don't have a future Mimas mission firmly planned in the way we have for Europa or for Enceladus-class targets. The body isn't at the center of any ongoing flagship program. So for the moment, the picture rests on the data already collected and on the models built around it. Now think about what mission targets the field has actually been pursuing. Europa Clipper, NASA's mission to Jupiter's moon Europa, is on its way and will study an ocean world that already has relatively strong direct evidence for its hidden interior. Future Enceladus mission concepts have been studied repeatedly, focusing on direct sampling of the plume material that the moon obligingly sends into space. Both targets reward investment because their oceans are loud. They leave signatures that close-up instruments can capture cleanly. Mimas isn't loud. A dedicated mission would have to work harder. It would have to do precision tracking, gravity science, and high-resolution imaging without the help of plumes pointing the way. That's harder to justify in a competitive science portfolio. So Mimas, even after the 2024 result raised its scientific profile, isn't yet in the mission queue. And here's a consequence worth being clear about. Without new direct data, our picture of Mimas will probably advance most through reanalysis of existing Cassini observations and through theoretical work that explores variations on the current models. Slow progress, refining the same evidence base, not the kind of dramatic new measurement that resolves a question. So patience is part of the situation. The picture we have now may be roughly the picture we have for some years, until a new mission is funded or a new analytical technique squeezes more out of the existing data. Now that isn't a final state, but it's a serious one. The current picture is the best reading of the strongest evidence we have, and that evidence is a combination of careful Cassini measurements and disciplined modeling work. So what the evidence supports in short is this. Mimas is no longer just the dead-looking moon with the giant crater. It may be an ocean world caught early in the transition. And that's the line the field is now defending, and the reading this argument commits to as the best current view. Not as proof, as the strongest available interpretation of the strongest available evidence. The honest part of the answer is the part that says this could change. New measurements could shift the balance. A future spacecraft could find features in the shell that we haven't yet detected. A new modeling result could open back up the non-hydrostatic core option. Knowledge in this domain rarely sits still for long. But what does seem stable, even under that kind of churn, is the broader observation. Surface appearance, on its own, is no longer a reliable shortcut to internal activity. Mimas has shown, in a way that other moons did not have to, that a quiet face can sit on top of a moving inside. So that is the idea the final question has to carry forward. Now return to the question at the start. How can a moon that still looks this ancient and inert be hiding a young global ocean only tens of kilometers below the surface? The answer, in plain language, is this. Mimas can look dead and still hide an ocean if the ocean is young, if the evidence for it is indirect rather than visible, and if the surface simply hasn't yet had time to advertise the change. So that's the answer, but it's not just an answer about Mimas. For most of the time we've been studying the outer solar system, The practical rule has been that surface activity is the main flag for internal activity. We see fractures, we see plumes, we see fresh terrain. Those are the moons we focus on. Quiet, cratered, ancient-looking moons are usually pushed to the side, treated as places where nothing much is happening. That rule has worked, broadly, for a long time, but Mimas is showing us that the rule has limits. A small icy moon, with no plumes, no obvious cracks, no fresh terrain, may still be in the middle of something significant. It may be hosting a liquid layer beneath its shell. It may be in the early phase of a thermal change that will, eventually, leave a mark on its surface, but hasn't yet. It may be a body whose past is fully on display, while its present is barely visible. So if that's the case for Mimas, it's worth asking which other moons might be in similar states. Now here's the move we have to make carefully. It's tempting to leap to the conclusion that every cratered icy moon could be hiding an ocean. That isn't what the evidence supports. Mimas isn't proof of a wide, hidden population. It's one well-studied case with multiple lines of evidence pointing to a particular interior and a specific story about why that interior may be young. So what it supports is a smaller, more honest claim. Some moons that look quiet may not be quiet underneath. The link between visible surface and active interior isn't perfect. There may be a transitional category, bodies whose insides have changed in geologically recent time, while their surfaces are still mostly records of the older state. We shouldn't assume, when we look at a heavily cratered moon, that we've already learned everything there is to learn about it. Now think about which moons might be worth a second look in this light. Tethys and Dione, neighbors of Mimas in the inner Saturn system, have been less intensively studied than Enceladus, despite being larger. Their orbital histories include similar resonance interactions. Their surfaces show varying degrees of preservation. Whether either has an interior story comparable to Mimas's is an open question, one that would require similar libration and orbital tracking work to answer. Beyond Saturn, smaller moons of Uranus and Neptune are even less constrained. Voyager flybys produced limited imaging, and no spacecraft has revisited those systems with modern instruments. Whether a Mimas-like transition is happening on any of those bodies undetected is genuinely unknown. The Vera Rubin Observatory and future targeted missions could begin to pick at this question, but the answers are likely years to decades away. So the lesson from Mimas isn't that we should go reclassify every cratered moon as a candidate ocean world. The lesson is that we should hold the surface-based shortcuts more loosely, and remember that some bodies require longer baseline measurements to sort out properly, and that's a real shift in how we read these worlds. Now think about the implications for how we plan future exploration. If surface signs aren't always reliable, then deciding which moons deserve a closer look can't rest only on visible activity. The motion of a moon, the evolution of its orbit, the shape of its libration, these are also clues, and they may sometimes be the louder clues. A moon that doesn't look interesting at first glance might become interesting when you measure it carefully over years. So that's exactly what happened with Mimas. The early imaging campaigns put it in the dead moon category. The careful astrometric and libration work pulled it back out. The story changed, not because we got better pictures, but because we got better at interpreting motion, and the future of this kind of work depends on being able to keep doing exactly that. Long missions in stable orbits, with careful tracking of where moons are at very high precision, repeat measurements over years. Modeling that combines surface data and motion data and shape data into a single coherent picture. Now picture a next-generation mission to Saturn. Such a mission could refine many of the numbers in the Mimas case. A closer flyby with more sensitive instruments could measure the gravity field in more detail, putting tighter constraints on internal structure. Thermal mapping at higher resolution could look for any subtle warm spots in the shell. Improved imaging could check for low-contrast features that earlier campaigns might have missed. If or when such a mission flies, the picture of Mimas could move from leading interpretation to something closer to direct confirmation, or it could shift in a different direction altogether. But for the moment, those are possibilities, not plans. The moon will sit mostly unstudied directly, while ground-based and archive-based work continues to refine the inferences. Now here's what makes this lesson feel genuinely new rather than just a minor adjustment. Before Mimas, the rough rule was, if a moon is geologically active, we'll see it. The cases that broke that rule were thought to be edge cases, detectable by other means. Mimas is showing us something different. A moon can be in the early phase of a major interior transition, developing a global liquid water layer, without having produced any surface sign detectable in standard imaging. The only clues are in the motion, and the motion only reveals itself after years of careful measurement. That's not a small methodological point. It means that the population of geologically interesting moons in the outer solar system may be larger than we've assumed. The quiet ones may not all be as quiet as they look, so hold the result narrowly. Mimas doesn't prove that hidden oceans are common. It doesn't prove that every cratered moon could be hiding one. It doesn't prove that surface appearance is meaningless. The cratered face of Mimas is still a real piece of information. It tells us about impact history. It tells us about the long quiet period of the moon's existence. It just no longer tells us by itself that there's nothing happening below. And that's the right size for the lesson, not a sweeping claim that overturns everything. A focused adjustment to one of our working rules. Some surfaces lag their interiors. Some moons can change in ways that don't show up on the outside, at least not yet. When we evaluate icy worlds in the future, that possibility is now part of the toolkit. Now here's a final thing to notice about this kind of result. It's not the kind of finding that thrills in the way a direct discovery does. No photograph of water, no plume captured in the act. The ocean of Mimas is, and may remain for a long time, a thing seen indirectly, but indirect isn't the same as imaginary. The ocean, if the current reading is correct, is a real layer of liquid water inside a real moon, whose existence we can read off the way that moon moves. We just can't, with current tools, walk up and look at it, a normal state for many of the most important things we know about distant places. Now think about how that fits into the broader history of astronomical understanding. The interior structure of the Sun was inferred long before any direct probe could be sent into a stellar atmosphere. The composition of distant exoplanet atmospheres is read from spectra of starlight passing through them. The presence of water ice on the Moon's poles was confirmed by orbital instruments that never touched the ice itself. In each of these cases, the science is real and the conclusions are reliable, even though the direct sample we'd ideally want isn't yet in hand. So Mimas's ocean fits into that pattern. Indirect evidence, well anchored in physics, supporting a specific configuration of the Moon's interior. That's the strongest kind of conclusion this branch of planetary science can produce given the tools available. New tools may eventually move it from indirect to direct. Until then, the indirect reading is what we have, and it's enough to update how we think about icy moons in general. So the cratered moon remains visually quiet. The crater is still there. The surface still looks the way the surface always has. Nothing in any picture of Mimas has changed. But after Cassini, after the libration work, after the orbital dynamics result, the silence on Mimas no longer means what it used to mean. The quiet, in other words, is no longer simple. So let the question come back one last time. How can a moon that still looks this ancient and inert be hiding a young global ocean only tens of kilometers below the surface? Now we have an answer, and it's bounded but specific. Mimas can look like a dead cratered moon and still plausibly hide an ocean because the ocean may be geologically young, inferred through motion and orbital behavior rather than surface spectacle, and not yet old enough to rewrite the outside in obvious ways. But the ocean isn't directly seen. Cassini didn't photograph it. No spacecraft has flown through a plume rising from Mimas. There's no sample. There are no fractures advertising the layer below. The case rests on careful measurements of how Mimas moves, and on what those motions imply when filtered through the physics of ice, heat, and rotation. So here's the line we have to keep clear. What we've measured is the surface, the shape, the libration, and the orbit. What we've inferred is the global ocean, the shell thickness in the range of about 20 to 30 kilometers, the recent age of the ocean in some range of millions to tens of millions of years, and the orbital scenario that probably drove the heating. The first set is close to the data. The second set is read through models. Both sets are real contributions, simply not the same kind of thing, and the most coherent reading, when we hold the measurements and the inferences together, is that Mimas hosts a global subsurface ocean beneath an ice shell of a few tens of kilometers, formed recently enough in geological terms that the cratered surface above hasn't yet fully responded. That reading isn't a guess. It's the interpretation that fits the libration, the orbital evolution, the physical plausibility, and the surface constraint all at the same time. Also conditional. New measurements could refine the numbers, narrow the age range, or open back up the non-hydrostatic core option. But what does feel durable, even under that uncertainty, is the broader lesson. Surface appearance on its own is a weaker guide to a small icy moon's interior than we used to assume. Some moons look the way they used to be more than the way they are now. Some surfaces are records of a long, quiet past, while interiors below have already begun to move. Mimas is the cleanest current example of that gap. Now picture the moon one last time. A small body orbits Saturn, far from the sun, lit weakly by reflected light. Its face is dominated by an enormous crater. Its surface is pocked with smaller craters. From a single image, it looks like a body that finished a long time ago. From a longer view, from years of careful Cassini data, from libration measurements precise enough to argue with the simplest model, from orbital evolution analyses sensitive to the deep interior, the moon is harder to dismiss. So the crater is still there. The silence is still there. The difference is that the silence now has a question underneath it. And if the strongest current reading holds, the question may be answered by a layer of liquid water hidden beneath the ice, recent enough in the moon's history that the outside hasn't yet had time to learn that the inside has changed. Mimas does not look like an ocean world. That, in the end, is what makes it interesting. If it looked the part, the question would already be closed. It looks the wrong part, and that's exactly why the answer, when it came, required a different kind of evidence altogether.